In section 2, we're gonna do the real math and just study the confidence interval. So recorded last time, or like in the previous part, like we talk about the concept of interval. Like given this big box of people or of population or of balls, and then we take some small samples. And then the goal is to use the information we get from that sample to to make an estimate of what the actual contents of this whole big box is. And we could achieve that by using the interval. But recorded that like last time there are two intervals. I did the big one that make us that is certain to append. Like we are 100% sure that the numbers are between 1 to 6 because we simply list every possible combinations. Right? But it is more useful to to narrow the range and make it close to the actual value. Right? But the trade-off is that we sometimes would be wrong, and depends on how you view like these two approaches. Like personally, I think this is like more useful. Like we have some small chance to be wrong, but the answer we get is better in the sense that we get an idea. Oh, it's like maybe 3 each. It's 2 to 5 versus the first case when there are like 6 possibilities, and now there are only 4 possibilities left. And so that's the interval, and the confidence is what we have on the right. And so the answer that we will get as interval will always come with the confidence. Like how confident we want to be. Do we want to be 100% confident and get a large interval? Or we want to get just get slightly smaller confidence in exchange for a narrower interval. And that's the concept here. Like pick your numbers on the right, and you can produce or you can get intervals on the left. And this is lots of text. I apologize for that. But let's there are 3 parts here. Okay, let's make that first. Okay, in the first part, this is a definition of a 95% confidence interval. So we talk about interval, and now we put the number for that interval, which is 95% or 0.95. The 95% confidence interval is an interval, and the yellow number we talk about just now, in which we are 95% sure, 95% confident that it contains the parameter, that the answer or the actual value we want to estimate is within that interval. So if we go back here, if we say 2 to 5, then that means we are 95% sure that the number of balls in the bag are between 2 to 5. So that's the confidence interval. And in practice, to compute or to generate that 95% confidence interval for the population with mean mu, that's the average, and the sigma. It's a deviation. It can be computed by using this formula. And at first, I know it's a badly looking formula. There are lots of variables, and there's this number, this mysterious number 1.96, which we will discuss later on where that came from. But for now, if you just want a single formula where you can plug everything you have from the problem into a formula to get the answer, this is a formula for you. And this formula is the closed interval, and the lower number is x bar, and recall that x bar is the oh yeah, I forgot to write here. X bar is the sample mean. Sample mean. Yeah, it is the word mean here. You get some sample and take the mean of those values, and then subtract that by 1.96, a mysterious number which we will discuss later. And then we have sigma, and sigma is, suppose it is known, because again the sigma usually, if you don't know anything about the population, then it should be impossible to get to know sigma. But suppose you get a better estimation of sigma, or maybe it is given, maybe something you knew from last year and you can use the same number for this year. Then that sigma is up to you. And then there's again a mysterious number, square root of n. N here is oh, I forgot to mention n. Like n, let's use orange. N is the sample size. So how many people you survey, or how many balls you pull from the back. That's n. And if you plug everything into the formula, then you get a single number out of it. And sigma is what you get from the sample, n is also what you get from the sample. Right? But this sigma is given in the statement of a problem. And there are two numbers here, like the lower end, on the left end point, like it's x bar minus this number, and the upper end on the right end point is x bar plus that number. So if you think about that in terms of a real line, then you get some number x bar in the middle, and then you have an interval that spans, it should be this one, span left and right, and the width of each side is this mysterious number, like 1.96 times sigma divided by square root of n. So you go to the left by by this amount, and then go to the right by this amount. And here we claim that we are pretty sure, like we are 95% sure that the actual mean, like the actual population mean, which we didn't know, it should be somewhere around here. So this is the answer in terms of interval. But sometimes, which I don't like, but sometimes in textbook they use this shorthand instead. So it's a number, the sample mean plus or minus this factor. Which again, this is just two numbers. It's not an interval. But the concept is the concept that the number is between these two values. It is within this interval. So and the some quick justification on why we have this kind of interval is because if we go back to the normal curve, either to the normal distribution, we have this curve. Actually, this should be hidden at first. We have this curve, and if you want to be 95% sure, or have the confidence of 0.95, that corresponds to making finding the area, finding the endpoints, these two endpoints, where the area is exactly 0.95. You have 95% sure, 95% chance that it will be correct. And there are actually some some tiny bits. I should want more explanations. This is actually the curve for the population mean x bar, but the question is why does it imply anything about the actual population? There's some hidden mathematical explanation behind that. But for now, for the quick explanation, I suppose we have this curve where the center is x bar, the sample mean. And actually this curve can be represented by the sample mean, that value, sigma over square root of n. Once you plot this curve, identify two endpoints where the area is about 0.95, then you would see that the these two endpoints, or like the width, is about 1.96 times the standard deviation, which is this number, sigma over square root of n. So it's about 2 standard deviation away from the center. So that's some short, quick, and of course incomplete explanation of how you derive that formula. So let's try to just use it. So in the actual problem, you are given this value. So suppose you use a sample size n equals to 100. So you pick 100 balls at random, and then we get the average of 122. Or maybe I should say about height of kids in maybe high school or grade school or something. And the average is 122. And suppose the standard deviation is known to be 20. Suppose we know the standard deviation of the whole school. And then find the 90% confidence interval. And in this quick example, like everything is given, formula is given, all the parameters are given. And so what you would do is you just use just apply the formula. Just apply the formula. The formula says that the interval is, if you think about I'm gonna write the image, write the graph on the right, but the formula says that okay, you take the x bar and subtract that by 1.96, multiply that by sigma, and then divide it by square root of n. And then x bar by 1.96 times sigma over square root of n. So that's the formula. And if you plug everything in, you should get x bar is 120, 2, it's 122, and 1.96, just keep it. Sigma is 20. So that's plus 1.96, and n is 100. So square root of 100 divided by square root of 100, and that's the answer. I wish you could simplify, because square root of 100 is just 10. 20 over 10 is 2. And so it's 1.96 times 2. 22 plus 1.96 times 2 again. And so the answer is let me look at my sheet. 118.08 and 125.92. That's the answer. An alternative notation, you said you can, again you could, but I don't recommend that, which is to write it as a plus or minus 1.96 times sigma divided by square root of n. And if you do that correctly, you should also get 122 plus or minus 3.92. That's an alternate way to express this. And what are these numbers in the way? Are the numbers? If you have to, and you should write a conclusion, you say that okay, we are 95% confident that the population mean, here the mu, that we didn't know, we want to find out, is in, oops, my head is in the way. We are confident that the actual population mean is in this interval. So that's the conclusion about the numbers that we just got. And again, we don't know what the actual population mean is, but based on this sample mean of 122, we are pretty sure that it's plus 122 plus or minus some numbers, like some small numbers. In this case, about 4. And that's the answer here. And if you want to visualize that, like the process behind this thing is that, oh, okay, you have this curve, like where the sample mean is 122. We have this nice curve that we can produce using this sigma and use this n. And if you want the area here to be 0.95, then these two endpoints 122 minus 3.92 and 122 plus 3.92. So that's the visual representation of what this formula is about. So we can, get some meaningful conclusion that, based on this 122, but based on this simple mean, like we could be, we could be confident that the mean, the actual mean, the population mean that we want to find out, it shouldn't be too far from that number. So that's one example. And actually, like in fact, if you have other examples, like they are gonna give you x bar immediately, they're gonna give you sigma immediately, they're gonna give you n immediately. So all you have to do is to just plug everything into this formula. And make sure that you understand, okay, what this formula is trying to tell you about the actual population. So that's one quick example. And then we move on to a more general case. Like the question you might ask is, why is 95? And that's a good question. we will answer that, I think, toward the end of this section. But if you want that number to be 95, like the formula is here, and that 95 will affect this number 1.96. If you change 95 to something else, like this number will also change. Okay, so that's a quick example, a quick application. But the question is, like, how if in case you are interested, in knowing how to derive this formula, like the question actually become something like, okay, given x bar by mu, something like that. And maybe just a quick quick explanation is that you want to find the probability that x bar minus mu, and there's some error, and this is the error, or the interval that we have, and that error, we want that probability to be 0.95, and that's why the 95% came from. And there are some other explanations behind why we need to use that sigma over square root of n, which you can also read from the slides. Right, but eventually, using all these things, we can conclude that we are looking for for the C value, where this area is 0.95, and it is the graph we have. If the center is 0, for the standard normal distribution, then we are looking for these two values E, where this area is 0.95. And that's how the formula got derived. And also, just a little bit, the reason why we have to go back and see how we get this formula about the area is because if you change the number from 95 to anything, to something else, then you're gonna have different areas. For instance, let's say if we want this area to be 0.99, we want to derive a different confidence interval, then can you guess whether the range E would be, the interval would be larger or smaller? Right? If you want the area to be enlarged to be larger, then from 95 from 0.95 to 0.99, then of course these values must be larger. Or the area is larger, so these two endpoints they must be further away from center. And so these numbers will affect how you can how you get this values e, or how you get the range of that interval. So this was for 95, but in general, like if you want the area to be anything else, like then the way you derive this is, and there are actually two ways, but the way the textbook use is okay. Instead of looking for the area within the region you want, maybe look at the area outside the region instead. So for instance, like if we go back to 95, if we want this area to be the 0.95, then that's the same as we want the tails. We're gonna use that notation like next class. I wanted to set the tails, like to have the total area of 0.05. We want the tails to be small. But since in this image you see that there are two tails, like that means each tail would have to be the area and the area of 0.025 each. So to get these two endpoints, you can either look at the area inside, which is 0.95, or look at the area outside the curve, which is 0.025 on each end. And so this is the general definition. Right, so if you want, they use the flip value, the let's say for the confidence interval of 0.95, you see that the tail and the sum of the tails are 0.05, because that's the area outside this curve. And again, since we know that the sum of these two must be 1, and if the middle is 0.95, then the ends must total to 0.05. And here in this definition, like this alpha is actually the small value, the areas outside this curve. And the reason why they use that is because first it's smaller, and usually smaller is better, and because you don't have to deal with large number. And also we think of these tails, these ends, as errors or outliers, or the small values, or the small chances that we can tolerate. Right? If you want to be 95% correct, then we want to be 5% wrong, 5% incorrect. And so usually we talk about that 5% number instead of 0.95. So here we're gonna flip that a little bit. In this definition, right, the alpha, that is the area of the tails. And since there are two tails, then the area for each tail is alpha over 2. And then we define z of alpha over 2 as the c value that cuts off a right tail area of alpha over 2. Notice the word right, like we're just looking at one end, and because they have the same size anyway. So that value, like, is a cutoff, it's this point. And formally, like, this whole sentence can be abbreviated to this equation. We want the area or the probability to the right, which is side of this point, to be alpha over 2. And that number is what we're gonna use to plug in to the formula. So in this case, sorry, we know that if alpha is 0.05, or if we want the confidence interval to be 25% confidence interval, right, then that will give you this value of 1.96. So that's how you get that 1.96. If you open the app, right, and use the app to find, okay, where's the point where this area is 0.025 alpha divided by 2, you would discover that this point is exactly 1.96, or not exactly, but I mean about 1.96. So that's the cutoff. We want the area inside to be like this big, like then that cutoff or that point must be that number. So that's the general definition. Like given any alpha, you can have small alpha, small tail, large tail, however you want to. Like you can get this cutting point. And then we have a general formula for the confidence interval. So recall that if you want 95% confidence interval, and actually I should start using the abbreviation of CI, like confidence interval. Right, then you need alpha to be 0.05, and then that value I see of alpha over 2 using calculator, you would see that this is about 1.96. So that's the special case with 95. But in theory, if you want that, if you want any size of confidence interval, in this case we want the confidence interval to be, or if you want the confidence interval to be 1 minus alpha, again a kind of flip, and 1 minus alpha confidence interval can be found using the same formula, except we have to change the number 1.96 to a new number correspond to this alpha. And there's a formula, and this formula estimate the actual population mean. And this they also have names, like this x bar is a point estimate, in the sense that we get this sample and we have that single point, so we start from that point. I start from the number we have, and then use the confidence level, like the width. Do you want the width to be wide or narrow? You want to be very confident and get a very wide range, or you would get less confidence but we get a narrower range. That's in exchange, and that's the margin of error. And again, that's the way we translate from the standard normal distribution to any normal distribution, and we call that the margin of error. I multiply that to the confidence level, and you create your own confidence interval. But in theory, in theory, you are not gonna use any random number. Like the most popular one is 95%, and they and the C value. Actually, I should also write that this is 0.025. It's about 1.96. But in practice, you're gonna use 95 a lot, and sometimes you wanna, increase the confidence to 99%. And then if you use 99%, then you're gonna have a difference which you can memorize. Or if you do enough statistics, then that number is gonna be embedded in your brain. And so in practice, you just gonna get a different number, and sometimes you want to be less confident, to get a narrower range, and then of course they're gonna give you another thing here, 0.5, another confidence level. And in practice, these three numbers are enough for you to compute the popular confidence interval. But in theory, the formula can be derived for any size of confidence interval. So let's see how we can actually find this confidence level in steps. So the steps there are actually several steps. For the first example up here, we simply have all the information and we have a single formula we can just plug in. But in practice, if you want a complete idea of how we can find confidence interval from scratch, then follow these steps. The first step is to, of course, to get samples in the first place and calculate x bar and calculate the sample mean. So that's the starting point. And for this section, we suppose that sigma is already known. The standard deviation is already known. In practice, you may have to compute this on yourself. But for this in this step, suppose it is known. Then we have to find the z-score. This is where we have to also establish. We have to to ask ourselves first what's the confidence interval we need, which is to get alpha, and to get the 1 minus alpha confidence level. The default number is 0.05, but you can get any number you want. Then for the z-score. Again, you can just remember these three numbers, or draw the curve by the point. Let's see, alpha over 2, where this area is alpha over 2. And the third step is to compute the error bound. So this error bound is this product after the plus or minus sign. This product we see here. So get the z-score. Use the z-score that we just got and multiply that by sigma and divide it by square root of n, the sample size. And then lastly, we can construct the confidence interval. Which is x bar plus or minus this error bound. Let's see, alpha divided by 2 times sigma divided by square root of n. That's the first step. And the final step is to make sure that you don't just give random numbers. So you write down the conclusion. Okay, we get some range, we get some interval. That's nice, right? But what does that mean? Why do we need this number? What can we do about this number? So write out the conclusion. Usually just a sentence that interprets what this is trying to estimate, right, in the context. Well, okay, we are 95% sure that the population mean is inside this interval. Stands. So these are the steps. Let's see if we can follow these 5 steps here in an example. So I think there are 2, right? Yeah. Oh, there are actually 3. Example 3. Suppose we have sample size n equals to 20 with a sample mean 125, and so with a known standard deviation of 20, find 90% confidence interval. Again, and in theory, all the numbers are given, right? And if you want to, just use the formula, that is the formula for you. Sigma over square of n. But suppose we, try to follow the steps. Right? Step 1 is to get the sample mean, which we got. Right? And maybe in step 1, you want to list all the numbers you you are given. Right? In this case, we have x bar equals to 125. Because sometimes the problem is given as a description of a problem. So they're not gonna tell you like x bar is equals to 125. Now they might say the sample mean is 125. So it might be, it may be more convenient if you translate that sentence into into a parameter. In this case, the parameter is given to be 125, and n, the sample size, is given to be 20, and sigma is 20, and also the alpha, like the confidence interval is 90. So we see that 0.9. Sorry, the confidence interval is 1 minus alpha. We want that to be 0.9 or 90%. And you can see that alpha is 0.1. So now we get all the numbers. And in step 2, maybe we find the c-score. The c-score. So again, visually we want this point. Let's see alpha over 2. And such that the area here is alpha over 2. So in this case, the area is 0.05. Right, and we can accomplish that by looking at this equation, which we learned last time how to find that. And suppose we know how to find that, or you know how to look up in the table, then you will see that this point is 164. So this one is 164. Okay, solving that gives you 1.64. And then the third step is to find the error bound. You can do 3 and 4 at once, because it's just a single formula anyway. But sometimes it's, if you want to compute the latter part first, and do that. So that is the formula. And that's z value times that. So that z value is 1.65. This is what we call the confidence level. And then the margin of error, which is sigma, if it's 20, divided by square root of n, which is square root of 20. Okay, so that's this number. I think you're gonna have to use your calculator to get the number out, which should be about 6.2. I think, if my note is not correct. Yeah, about 6.2. And lastly, you can find the interval. This simply say that you pick x bar, which is 175, and add and subtract that by the error bound. The full formula is that, but we can plug everything we have. 175 plus and minus 6.2. And so that's a shorthand notation. But you try it in terms of an interval, you get an interval of 168.8 and 181.2. So that's the final result. I think we choose this pink, I guess. 68.8 and 181.2. And that's the answer. But lastly, you should say a word about what this interval is about. We say in this example, we say that, oh, we can say that with 90% confidence, we are 90% sure that the, I think I should move this part down. Okay, yeah, we can say that with 90% confidence, the population mean is in the interval that we just got, which is from 168 to 181.2. So that's the complete step of deriving the confidence interval and say something about it. But again, it's just a single formula, but this can be broken down into small steps. So this is the way to solve it in details. And also in future, like now you know that, oh, whenever you want to compute 90% confidence interval, you can just use 1.64. But this step is fixed. We use the standard normal distribution to get 1.64. So every time you want to compute 90% confidence interval, you always gonna use 1.64. And that's what I mean by, memorizing these numbers. 1.64. Oh, and again, it makes sense, right? Because the confidence interval, we want to be less confident, and so we get smaller, or we get narrower length of the interval. So that's example 3. And let's finish the rest, because I think, yeah, the rest have the same setup, the same sample size, the same sample mean, the same standard deviation. The only difference is the size of the confidence interval. In example 3, we have 90% confidence interval. In example 4, we have 95% confidence interval. So everything will be the same, except that this 1 minus alpha is 0.95. So alpha is 0.05. This means we go back to the table, to an app, to whatever you have, to find the point, like this point, this counting point where the area is alpha over 2. You use calculator or whatever, you will see that this number is 1.96, which is the number we are given, like in the first place, 105% confidence interval. And so the answer is, of course, using the same formula. That's a single number. Like x bar is 125 plus or minus this one, 1.96. Sigma is still 20. N is still 20. We get this new interval. And I think it's 125 plus or minus 8.76. Or in terms of an interval, we get 166.4 and 183.76. So here we are more confident, right? But that's because we increase the length of the interval. Then again, if you want to write a conclusion, you will say that, okay, we are 95% confident that the population average or the mu is in this interval. The similar conclusion, I just change the level of your confidence. Okay, so that's example 4. And lastly, for example 5, the same setup. Like n is 20, mean is 125, x bar is 175, sigma is 20. but now we have 99% confidence interval. So again, 1 plus alpha is 0.99, and so alpha is 0.01. Maybe we want the error to be only 1%, and that point then again can be found. Okay, if you draw the curve, you find a point where the area here is alpha over 2. Use an app or use whatever you want, and the answer should be 2.57, which is pretty high. But nevertheless, you plug that into the same formula times sigma divided by square root of n. You get 175 plus minus 2.57 times 20 divided by square root of 20. It gives you 175 plus or minus 11.49. And the range is now 163.51 and 186.49. So again, the conclusion would be that okay, we are 99% sure that the mu is inside this interval, and we increased our confidence because we increased the length or increased the possible values for mu. And so that's the end of the way you compute the standard confidence interval. And there are some remarks here that you may notice from doing these 3 examples. The first remark or the first note is that the higher the confidence level is, the larger the interval becomes. Again, like this corresponds to the way that, oh, if this is the probability, like if you want the probability to be high, like then you have to, pick the points to be first point. And then the further the point is, the higher the area is, and so you get a higher confidence level. And second, like since the normal distribution curve extends to infinity, like both left point, as you can see from the curve, like the left endpoint and the right endpoint actually goes on forever. Like it doesn't stop here. If you have to be, technically correct every time, I would have to put arrows on both sides. But that's in a way. So in theory, like the arrow extends forever. Right, so we cannot find a point like that. We cannot find a point where the area is 1. Right, because whatever point you pick, like there are some areas on the right and on the left of those points. Always. And so it is impossible to find the cutting point or to find the z value where the area is 1. And that implies that it is impossible. No, we can never say that we are 100% sure, we are 100% confident that the population mean is within this range. And because there's always some chance that we could be wrong, no matter how small that chance is. Actually, you could say that if you say, okay, we are 100% sure that the number is between minus infinity and infinity. But again, that's nonsense. And so in practice, if someone claims that they are 100% sure, then you should start to doubt them about, are you sure? And lastly, like the reason the 95% or the number 0.95 is prevalent, you see it everywhere, it's because it seems like the nice balance like between the amount of confidence and the width of the interval. Because notice that if the confidence level is small, then you get the range is narrow. Let's say 90%. Like 90% seems small. Again, it depends on your perception, but in statistics, 95 is small. 1 out of 10 is nothing. Like it could happen. For 95% chance, it's slightly wider. But let's say if you increase that to 99%, which is the number that we want. But the bad news or the trade-off is that you get the interval that is too wide. This will be too wide. So for 99% interval, give the interval that is too wide to be useful. But 90% confidence interval give a narrow one, but the chance to be incorrect is high. And so that seems like a striking balance. Again, is objective. That's the end of the second session of what is confidence interval and how you could compute it. And in the next section, we will see a more complicated formula that is used to find other types of confidence intervals.